Welcome, geometry students. This is going to be our snow lecture. I'm recording this on Ash Wednesday, about noon. I had a meeting with Mr. Price just a little while ago. We may not be in school tomorrow or even Friday, so this will tide you over until next we meet. We're on the chapter in right triangles, and I just want to give a good overview of what we've done and what you're expected to be able to do and give you some practice problems so that when we get back together again, everything will be okay. The first section was on the proportions, and I think we've pretty good on that, proportions in a right triangle. The whole idea of the geometric mean, so if we had a sketch of a right triangle in here and we drew an altitude, I guess I should probably draw a nice right triangle there. Okay, so that's a right triangle. There's my right angle up there. And then if we drew an altitude down, you would say that this altitude is the geometric mean between these two pieces of the hypotenuse. So if you thought of a proportion where you have this ratio, you would have the altitude would fit in here as the geometric mean, and the other two pieces of the proportion would be the piece over here, that piece, and then this piece down here. Okay, so that's the first proportion that you needed to be able to do. And of course, you know, we can make some problems there. If this is x and this is 3 and this is 5, you would say 3 is to x as x is to 5. Cross multiply 15 is x squared, so x is the square root of 15. Okay, so that's the first proportion that you needed to know how to do. But then there was another one as well, and it also had to do with dropping an altitude to the hypotenuse in the right triangle. But now we had a slightly different setup. We noted that the leg, let's make this one dark here, the leg of the right triangle is the mean proportion between its projection onto the hypotenuse, think projection coming down, and the entire hypotenuse. So the leg is the mean proportion. Again, sort of think of a proportion here. So here's my equal sign. And the leg, the red leg, is the geometric mean, or the mean proportion, between its projection and the entire hypotenuse. So if we have some numbers in here, again, a quick example, let's suppose the leg was 8, and this much right here, this blue bit, was 2, okay, and the entire leg was 12, just to pick some numbers out. Okay, so what you would find, well, I guess we should probably call this x. Let's call this x. Okay, so here's our proportion, and the x is going to go here as the geometric mean. The projection is 2, and the entire hypotenuse is 12. All right, so cross multiply, and you get 24 is x squared, so x is the square root of 24. And you should probably clean that up, 2 square roots of 6. Okay. So there's an example, 2 examples, and there's nothing magic about this leg. It can also be true with the other leg. So let's just sort of flip this to this side. That leg is again the mean proportion. And again, we're going to have its projection coming down and 12. But now notice that things are a little bit different. You're going to, let's again call that leg x. It's going to fit here in this geometric mean slot. So now our proportion looks like this. X is here and here. And the projection now coming straight down is not going to be 2. That was the projection of the other leg. the projection now is going to be this much. So if we knew that this bit was 2, say we were given that information, then the projection coming down, the blue over here would have to be 10, right? Because 2 plus 10 has to add to 12. So 10 would go there, and the entire hypotenuse is 12, right? So x squared is 120. So x is the square root of 120. And again, you should probably clean that up a little bit. Let's see, 120, 2 goes into it, and 2 goes into that. And what have we got? 2 goes into that, and then 3 and 5. Now I only see a single pair. So x is 2 times the square root of 30. Okay, so that would be a good way to finish that problem given that picture. Okay, the second lesson in this chapter was all on the Pythagorean theorem. So make sure you know how to work the Pythagorean theorem. And we've been doing this since the beginning of the year, so this should be pretty easy now. The new thing in this particular chapter was that there are certain integers that will be called Pythagorean triples. And you should be on the lookout for right triangles that have sides of 3, 4, and 5. So this is a common triangle, 3, 4, and 5. The next Pythagorean triple that you should look out for is the 5, 12, 13. And again, now a little bit longer going this way, but this would be 5, this would be 12, and this would be 13. Those numbers, 5 squared, right, 5 squared plus 12 squared is 13 squared. Okay, the next largest Pythagorean triple is the 7, 24, 25. And again, you can imagine a long triangle like this. This is 7, this is 24, and this is 25. So if you're just be on the lookout for those, there's a whole list of them in your book. I think if you know these 3, you'll be in good stead. I don't think you'll see, much beyond this. The next few, if you just wanted to note them, would be 8, 15, and 17, 9, 40, 41. But in general, when you run into a right triangle, expect to get sides that are not integers. So when you have your generic right triangle, right, with just a couple legs given, use the Pythagorean theorem to solve the triangle. So if this is 2 and 3, and you need this hypotenuse, you know that 2 squared plus 3 squared is x squared. So 4 plus 9 is x squared. X squared is 13. So x is the square root of 13. Okay, and that's going to be the case most of the time where you get irrational legs or the hypotenuse. And again, be able to work these, whether I give you the 2 legs and you're looking for the hypotenuse, or whether I give you the hypotenuse in one leg and you need the other leg. That's the other type of problem that you would see with Pythagorean theorem problems. So let's suppose I told you this was 6 and this was 4, and I ask how much is that? So again, set it up. You square the legs, x squared plus 4 squared, add them together, and that has to be the hypotenuse squared. Okay? So x squared plus 16 is 36. So x squared is 20. So x is the square root of 20. And you should clean that up as 2 square roots of 5. Okay. So x now is 2 square roots of 5. Okay, Pythagorean theorem. One particular diagram that I liked in this section was if you had a right triangle with 2 legs that are exactly 1 each, and you're asked to find the hypotenuse. Well, this would be the square root of 2, right? 1 squared plus 1 squared is x squared, so 2 is x squared, x is the square root of 2. Suppose, however, I now drew another right angle here, and this is again length 1. Okay, so how long would that be? So now you know that this leg is the square root of 12, and this leg is 1. or sorry, square root of 2 and the leg of 1. So you would square the square root of 2, which is 2. Square root of 2 squared plus 1 squared would give you this particular hypotenuse over here. So the square root of 2 squared is 2 plus 1. Let's call that x. So x is the square root of 3. This now becomes the square root of 3. And if I continued this idea, so I drew another right angle here, and I made this 1. It's about the same. I made that 1. And so now the task is how long is this? So you would square the square root of 3. This one was the square root of 3 here. Okay. Square root of 3. Square that, that becomes 3. You would square the 1, that becomes 1. 3 plus 1 is 4. So this now is the square root of 4. Okay. Square root of 4. So it's sort of interesting. This hypotenuse is the square root of 2. This one's the square root of 3. This one's the square root of 4, which I know is 2. That's obviously the number 2. And if I continued spiraling around, always making a right angle, this would be the square root of 5. And then this one would be the square root of 6. And another right angle, all of these being 1s. This would be the square root of 7. And you could just keep going forever this way if you want. This would be the square root of 8. Right? And by the time you got to here, now you're up to the square root of 9, which is 3. So there's your right angle. And so play with that one for a little bit. Okay, Pythagorean theorem. The next section in the chapter dealt with special right triangles. Special right triangles. And these were denoted as 30 degrees, 60 degrees, and 90 degree triangles, or also 45 degree, and 90 degree. They're all right triangles, obviously, so you have the 90 degree angle, but 30, 60, 90s. And for these, you needed to know some particular ratios. Let me draw. This is representing our 45, 45, 90. And this is our 60 down here. There's 90, and there's 30. That might be a little bit skinnier if I were to draw that a little bit more accurately. There. Okay. So 60 degrees and 30 degrees. Okay, now what are you supposed to know on these? Let's see, let me pause this here for a sec. Okay, back to the 30, 60, 90, and 45, 45, 90. The key on these is you need to know that if you're given a side, let's say this is 5, that you don't need to use the Pythagorean theorem. You can, but it's much quicker just to write the hypotenuse as 5 square roots of 2. So going from a leg to the hypotenuse, when you have these 45, 45, 90s, you just take whatever the side is and multiply by the square root of 2. If this happened to be 15, the other leg is obviously 15. It's an isosceles right triangle, and this is now 15 square roots of 2. Okay, so 45, 45, 90 is easy to go. The second part of this particular triangle is what happens if I give you the hypotenuse. Suppose I gave you this as 7, and now you're going to go to the legs. Well, obviously, multiplying by the square root of 2 is going to be too large. So the square root of 2, by the way, is about 1.4. So we certainly don't want to make this any longer. This, after all, is the hypotenuse. The legs have got to be shorter than 7. So we still use the square root of 2, but we do it this way. 7 divided by the square root of 2. So 7 divided by the square root of 2. And that will get us to the 2 legs. Okay, so from the leg to the hypotenuse, multiply by root 2, and from the hypotenuse to the leg, divide by root 2. That takes care of these. 30, 60, 90s are a little bit more interesting, but again, we have sort of the same idea. If I give you the hypotenuse, let's say I told you this was 8. Now, one of the things I really like with these 30, 60, 90s is if you envision, you sort of have to use your imagination here, envision an equilateral triangle. Now, you know that an equilateral triangle would have 3 60-degree angles. There would be one in this corner, one in this corner, and one up here at the top. And then if I cut the equilateral triangle right in half, that helps you figure out this particular leg. Okay, so I gave you the hypotenuse was 8. This leg has got to be half of 8, right? If this were an equilateral triangle, this would be 8, this would be 8, and this would be 8. So the short leg here is always going to be half as much, 4. So 8 to 4. Okay? Now let me back off most of that and just look at our equilateral, our 30, 60, 90 again. And this is what you need to know. I give you the hypotenuse. The short leg is half of it all the time. Hypotenuse to short leg, cut it in half. Now, to get to the middle leg, or this longer of the two legs, you're going to take 4. You're going to take this number, but you're going to lengthen it out by this amount, right? Multiply by the square root of 3. And just for reference, the square root of 3 is about 1.7. So it's not twice as long. Remember, the hypotenuse would be twice as long. This is going to be the short leg times the square root of 3. And again, you could work all of these using the Pythagorean theorem, but it's much, much easier if I just give you the number that you immediately write down the answers. If this is 7, this is going to be half of that, 7 halves, and this is going to be 7 halves times the square root of 3. Okay? So sort of in comparison to this one, there's the square root of 3 appearing, not the square root of 2. Okay, now suppose I'm still looking at this 30, 60, 90, but this time I don't give you the hypotenuse, I give you the short leg. So that shouldn't be terribly hard. In fact, it's probably a little bit easier. Suppose I told you this was 10. Now the hypotenuse has to be twice as much, and this one just has to be 10 square roots of 3. Okay, so that's not too bad. The trickiest one, I suppose, would be if I gave you the longer of the two legs, and you had to find all 3 of them. So let's suppose you were given this longer leg as 6. Now, the square root of 3 still appears, but it doesn't make any sense to multiply by the square root of 3. Instead, we're going to divide by the square root of 3. Okay, so you're dividing by about 1.7. And then to go to the hypotenuse, this is always just going to double it. So 2 times 6 over the square root of 3 is 12 over the square root of 3. Okay, so that's the hardest one to play with. But certainly you should practice these. They're all in your book. I'll put together a worksheet this afternoon and let you try finding sides of 30, 60, 90s and 45, 45, 90s. Okay, the next section in the chapter was all about these trig ratios. Trig ratios. And in a geometry class, we're not really doing a lot of trigonometry. You need to know that the tangent of an acute angle, and I'll use the Greek letter theta, is the opposite side divided by the adjacent side. And because this is a right triangle, we can say the opposite leg, if you will. These are going to be the legs of our right triangle divided by the adjacent leg. A lot of times in trig class, we just say side, and I'll use both those interchangeably. Okay, now what do I mean by that? I mean, if I give you, let's say this is our 5, 12, 13 right triangle, just to use one of our Pythagorean triples, and I call this angle down here theta, then the ratio, the tangent of that angle, the ratio will be 5 over 12. That's the opposite leg. So think about going opposite, that's 5, and adjacent, which means next to. Okay, adjacent leg, opposite, adjacent. So 5 over 12, that's the tangent of that angle. Let me back some of that off. Again, we still have this same triangle, but now let's look at this angle up here, and because I don't want to use the same letter, let's call that one, I don't know, phi, another Greek letter. So if I want the tangent of phi, it's an acute angle in a right triangle, you need to use the opposite leg, so go across the triangle. So that's 12, and then the adjacent leg, which is 5, so 12/5. Okay, so that's how you would use that tangent ratio. Now, what can you do with it? Well, there's a number of things that are pretty useful. If I wanted to find, say I wanted to find how much this angle was, let's go back to this one down here. We'll call it theta again. So the tangent of theta was 5/12. If I wanted to actually figure out how large that was, the calculator does that. Now, when you turn on your calculator, make sure that it's in degree mode. If you have a choice, it has to be reading degrees. And a good check is if you just hit tangent and you hit 45 and enter. If it comes up 1, then you're in the correct mode. If it comes up something other than 1, you're going to have to figure out where your mode is. For example, if this were in radian mode and I tried the tangent of 45, I don't get 1. I get this strange 1.619. Okay, so that just tells me that I'm not in the correct mode. Okay, assuming we're in degree mode and I want to figure out how large this angle theta is, I'm going to solve this equation for theta. Now, this is not a multiplication problem, so I'm not really dividing. What I'm going to write is theta is the tan inverse, and that's the way you would read that, the tan inverse of 5/12. And the way you do that on your calculator, the tan inverse button is second tangent, and it looks like a -1 exponent. It's not an exponent. It's just called the inverse tangent. And then you put in your 5/12, and then you hit enter. And so this is about a 22-degree angle. And, you know, how close do you want? I sort of like to go to the nearest thousandth, so 3 decimal places, 22 point, what's that, 620 degrees. Round it to the nearest thousandth. And you should be, you know, fairly comfortable with that. The calculator said 22.619864. Okay, so thousandth place, this is tenth, hundredths, thousandths. To decide what to do with that, we look at the next one. It's larger than 5, or 5 or larger, so this has got to round up. So this becomes a 0, which kicks this one up to a 2. Most calculators will do that for you. If you look under mode, and if I put this in 3 decimal point mode, like that, and then try the same problem, the tan inverse of 5/12, it will round it for me, 22.620 degrees. Okay, so there's the tangent ratio. The other two that you're supposed to know are the sine and the cosine ratio. Both of these, the sine of an angle is the opposite leg divided by the hypotenuse, and the cosine of an angle is the adjacent leg divided by the hypotenuse. So maybe a quick picture or two will show you how that plays out. These have to be right triangles. This is going to be 70 degrees, and I want to figure out how long this is. I tell you, this leg is 3 inches. Okay, so that's the task, 3 inches. How long is that? Now, if I look at my ratios, here's my angle, 70 degrees, and this is now the adjacent side, and this is obviously the hypotenuse. So the way I would play with this is to look at this cosine ratio, and I just put in all the stuff I know. The cosine of 70 degrees, that's the angle, is the adjacent side, which is 3 inches, divided by the hypotenuse, which is x. Now, solving equations like this can be a little tricky. What I like to do is to consider this as the cosine of 70 over 1, and then take this proportion and just flip both ratios upside down. So call this the upside downable theorem. Take the ratio on the left, turn it upside down. Take the ratio on the right, turn it upside down. And then generally, this equation is much easier to solve. So to get the x by itself at this stage, just multiply both sides by 3 inches. Right? Okay, so x becomes 3 divided by the cosine of 70 degrees. And the units will be in inches. And to do that on my calculator, 3 divided by the cosine of 70 degrees. and I get 8.771 inches. So this length, this hypotenuse, 8.771 inches. And that's an approximation. You can be more accurate if you like, right? But given the information that we have, that's what I would do for that problem. Okay, so that was one using the cosine. Let's do a sine problem. And obviously, you can stop these and play these back. For the sine problem, let's do this. Suppose now I give you a triangle, and this is my right angle. And now the task is you're going to have to tell me how much this angle is. I'm not going to tell you that, but I will tell you that this is 12 and this is 13. So hey, maybe this looks like our 5, 12, 13 triangle again. And so now the task is how large is this angle? And again, note that this is opposite and this is hypotenuse, and that uses the sine ratio. So the sine of this angle, now I'm calling it phi, is going to be 12/13. So phi is going to be the sine inverse of 12/13. And you'd use your calculator to find that. Okay, so second sine, that's the sine inverse, and then put 12 divided by 13. Okay, so 67.380 degrees. So phi is about 67.380 degrees. Okay, so you can use the trig ratios to find the sides, or you can use the trig ratios to find the angles. And again, I'll put a worksheet together and get you lots of practice on these before we come back to school. And it may not be on Thursday or Friday, it may even be next week, who knows. Okay, the last thing in this chapter was slope. And the big thing on slope, this remember is a review of algebra. This is rise over run, rise over run. And just think if the line is horizontal, the slope is 0. If the line is rising to the right, the slope is positive. We use the letter M for slope. If the line is falling to the right, then M is negative. And all of these problems are what's called analytic geometry. You would be given a couple of points. So this is the ordered pair, 3, 1. And here's another ordered pair, -1, 5. And the task is, what is the slope of this line? Now, why is it in the right triangle section? Well, because this, obviously, if it's on a grid, it forms a right triangle. And you should be able to find the slope of that line. Okay, so let's figure out how long these sides are. This is 4 long down here, right? And this happens to be 4 long down here. So this is our 45, 45, 90 triangle. And so the slope is the rise, when in this case it's a -4, right, going down, not rising, but falling. And running is 4, so the slope is -1. This 45-degree line that goes through these 2 points has a slope of -1. Okay? Now, I didn't ask, but if I wanted to know the distance between these 2 points, you should already know that because this is a 45, 45, 90, 4 square roots of 2. That would be the distance between the 2 points, or the length of that line segment. But yeah, you should be able to work with slopes and the triangle that results. They're always going to be on the grid, and the lengths and the angles. One more slope problem. Let's suppose we had a line that was going through the ordered pair 2, 1. And let's say the slope was equal to 3/5. So from here, I would go up 3, 1, 2, 3. That puts me here at 2, 4, right? Because I'm going up 3 units, 1, 2, 3, 1, 2, 3, 4. So that's that. But now I would want to run 5 units. Remember, this is rise over run. So from there, I have to run 1, 2, 3, 4, 5. That puts me over to here, right? Going 5 units to the right. So we went 3 units up, 5 units to the right. This is the ordered pair 7, 4. And just double check. 1, 2, 3, 4, 5, 6, 7. Right? So here's our line. It has the correct slope. Right? Correct slope is 3 over 5. And it goes through this point here, 7, 4. And it started at this point down here, which was 2, 1. Okay, so what are you supposed to do with this line? Well, you can do all sorts of things with it, you know. For example, I could ask you, how long is this segment? That would be a pretty easy thing to do if you knew that this was a right triangle, and this much is 3, and this much is 5. Okay, so use a good old Pythagorean theorem. Call this x just for a minute, and you get 3 squared plus 5 squared is x squared. Right? So 9 plus 25 is x squared. So x is the square root of 34. That would be how long that is if you needed it. Suppose I wanted to know how large this angle was. So what's that angle? Well, let's see what we know. We know the opposite side is 3, and we know the adjacent side is 5. So that harkens to tangent. We know the tangent of the angle is 3/5. So the angle would be the tan inverse of 3/5. So we can grab our calculator and hit the tan inverse of 3/5. Okay, so that's going to be a 30-degree angle, almost a 31-degree angle. So the angle theta is about 31 or 30.964 degrees. Okay, what else could we do? Well, if we know our algebra, we can find the equation of this line. Right? To find the equation of the line, probably the most useful form here is called the point slope form. In your book, check. You should know this is from algebra, and this is a little review here. The point slope form of a line requires a point, and it requires the slope. Here's the formula: y minus y1, m, that's our slope, x minus x1. And obviously the slope for this problem was 3/5. That's going to go there. And the point, well, we have a couple of points. Well, let's do this point here. We'll do 2, 1, simply because the numbers are a little bit smaller there. 2, 1. And those coordinates fit in here. This would be the 2, and this would be the 1. Okay, so if I wanted to clean this up a little bit, the equation of this line, y minus 1, is equal to 3/5 times x minus 2. And there you are. If you wanted in slope-intercept form, you could do that. You'd have to do some simplifying here, but I'm real happy with this. This is the equation of the line. And now someone's going to ask, but why did you use that point? Could you have used this other point up here? And I answer, yes, you can. You would get the equation of the line using that point. Let's see how that would fall out. So here we are, y minus y1, m times x minus x1. The slope is still 3/5. I'm not going to change that. Now my x-coordinate way up there on the top is 7. And my y-coordinate way up on the top was 4. And so this also works as the equation of the line. Now, some students look at those and go, they can't be right. They look different. Well, they really are the same line. Again, let's do a little bit of simplification. This is 3/5 x minus 6/5, right, distributing. And then I'll go and add 1 to both sides. So 3/5 x, now I'm adding 1, right? So this is minus 6/5, but I'm adding 5/5, right? Adding 1 to both sides. So I have y is 3/5 x minus 1. fifth. That's slope-intercept form. If I want to play with this one the same way, surprise, surprise, y minus 4, 3/5 x minus 21/5, again distributing. Right? And now I'm going to add 4, so y is going to be 3/5 x minus 21/5, and I'm adding 4, which is 25th, that's 4, right? So sure enough, exactly the same equation that I got using the other point, minus 1/5. Okay, so again, some practice problems with proportions, the Pythagorean theorem, 30, 60, 90, 45, 45, 90, and then the trig ratios and slopes. Hope you brought your book home. Okay, let me stop this right there.